Hello, and welcome to the Unretired Engineer and how EVs ate my job. So, in June of 2025, I received the call that employees dread from HR saying that my services were no longer required, and thank you for all your good work. The company I was working for had been working for since 2016. Was going through a massive reorganization, so it was not terribly surprising, but it was disappointing. I'd enjoyed my job, I enjoyed the people and technology, and I thought the company was a very good company. But the environment it operated in had kind of cut its knees out from under it. And EVs were the proximate cause of that. And we're going to talk about that. EVs themselves are the transportation of the future. They are not going to be the only piece of that transportation infrastructure, but they're going to be a big piece. They've been held back for a long time by battery technology and other technology and infrastructure. That has meant that they really weren't a practical solution except some very niche markets for a long time. But that has changed in the last few years, and they are going to take over from the internal combustion engine. They do make more sense in some ways, but they also have limitations. And we're going to talk a little bit about both of those. So an EV has a big advantage in that it's a relatively simple machine with a battery, a power conversion unit, and a motor, right? The motor turns the wheels, the power conversion it mediates between the motor and the battery. So most of the time driving the wheels, sometimes regenerating. EVs being relatively simple and only rotating machines has meant that they've had a long history from the 1830s to today. They've existed and they competed before the internal combustion engine could compete for on the road. So there were steam vehicles on the road and there were electric vehicles on the road, and then along comes the internal combustion engine, and it was a better solution. For a long time, that was kind of an ongoing discussion, but by the early part of the 20th century, the EV was falling away. And by the time I was a kid, basically in the 60s, you didn't see very many electric vehicles. The ones you saw were, I saw milk floats, right? So the milkman doing his daily delivery. And those were very slow, but they were stop-start. And they also only operated prompt during the morning hours, right? By midday, they were done with their rounds and they would then go back and recharge for the rest of the day. So slow charging, short range, none of that made any difference, right? So the other area was things like forklifts and in-factory type vehicles and golf carts in some applications, right? Those all made some sense for a variety of different reasons, no emissions. The battery's weight didn't matter, slow speed, slow charging, none of that really mattered. It was really the performance and simplicity of the vehicle that dominated, and those vehicles made sense. So a long time, the battery really was the limiting factor. You could say the electronics to drive the motor was an issue. Motors were heavier back in the day, but those didn't really matter that much. It was the battery and charging and infrastructure to charge that were the issues. When I was a little bit older and I was a student in college, EVs were a big part of a lot of people's student life, right? Several programs when I was at college, people were working on EVs of various types, looking at range, looking at the battery technology, looking at motors, but essentially it was a toy, and it was a good toy in some ways because it was simple, right? And it was relatively easy for us to measure the performance. So it was kind of fun and didn't do any harm and improved the technology. So moving forward, the California Air Resource Board got on the bandwagon for zero emission vehicles, which really effectively means electric vehicles. And in the 80s and 90s, they put in a series of regulations that said if you were going to sell vehicles in California, you had to sell a percentage of zero emission vehicles, which meant electric vehicles. And you had to do it not just to special interests, but you had to sell to the public. This spawned the GM EV1, which was a very pretty car, but wasn't very practical because it took a long time to charge. Its performance was good, but it wasn't exactly a golf cart. But it wasn't brilliant because the range was really short, so it was really only good for about town. And then the other one was the Chrysler minivan, maybe a bit more practical vehicle, but again, very short range, not very slow to charge. So really not practical as a general purpose vehicle. This was recognized, and those programs essentially went away. The regulations slipped, and they kind of went away for a while. But in that period, there was investment in technology, motors and drives and things like that. I worked in that area. I was looking at silicon devices for improved performance for a variety of things from a military perspective, but with a very big Department of Transportation, Department of Energy kind of bias as well. So there was a lot of work going on, batteries and motor drives and motors to an extent. And so technology was moving forward. But one of the things that was, I think, spawned a little bit by GM EV1 was electric vehicles could be pretty, sporty looking. It didn't have to look like a cardboard cutout or a golf cart. It could be fancy. The other is technology in batteries had really started to evolve. People hadn't seen it that way because the battery technology that had really made advances, the lithium-ion battery, were intended for portable electronics. But, well, okay, you can call a car portable electronics, right? You just have to put a lot of those batteries. And that's what Elon Musk did with Tesla, right? The Tesla Roadster. So he took a very pretty car, put a lot of those batteries in it, took the state-of-the-art power electronics and motors and put them in there, came up with a vehicle that was a premium performance and premium feel to it. And that gave him an into the market that he then moved in with the Model S and then the Model X. And, and basically pushing, people were interested in a vehicle that was reasonably practical, had a reasonable range, a couple of 100 miles, and good performance and looked good, right? And felt good and gave you the good feel when you were inside. It wasn't a tiny little box. So it really was a good vehicle. So he really made inroads. He really made a breakthrough, and a lot of other people followed him, whether they were already going down that road or not, who knows? But he was really the leader. He took advantage of it. And the other thing he did was that he really wrapped a new industrial manufacturing ethos around building those vehicles, which I think is paying huge dividends to this day and moving us forward a lot in technology. So batteries had a huge inroads, but at the same time, there was an awful lot of government and non-governmental, thumb on the balance to push EVs. And, everybody was saying, we have to do this, we have to do that to get net zero, all the rest of that. So a huge investment throughout the automotive industry was thrown into EVs, even though a lot of the engineering staff were resistant because, from an engineering perspective, there are a lot of issues with moving rapidly into an EV. But if the government says you have to and they're paying you to some degree to do it, you do it. And that's what happened, right? So the electric vehicle market took off in the early 2020s and a little bit before that, and started to really make some sense because the technology had reached a point where it was quite feasible to build a very practical electric car. But one of the technologies that had done that was a technology I was working on, had been working on for some years, which was silicon carbide. So just for background, silicon carbide is a semiconductor. It is the second hardest material on Earth. If you have seen silicon carbide around, it's usually you will have seen it as the abrasive compound on good grade sandpaper. That's same silicon carbide. But when you're talking about a semiconductor, you have to turn that sand basically into huge sheets of single crystal. So you have to melt this extremely hard, high temperature material down, and then draw what's called a boule of that material as a single crystal. One huge single crystal you then slice into wafers. This is what you do with silicon, right? Silicon can be used as processors. Back in the 80s, 90s, early 2000s, I did a lot of work in that area using silicon, right? But it has severe limits. It's the voltage withstanding, the amount of volts that it can stand off for a given thickness of material is much lower, and the inherent conductivity that you can make in the device is much lower, so it becomes basically a very low value resistor when you're flowing current through it. So it generates a lot of heat, and oh, by the way, it doesn't like heat, you know very well, right? You don't want to get your electronics higher than about 85 degrees C, after which it'll start, doing bad things. Well, that's, a severe limitation when it's self-heating very, very easily. So it's not a great power device. Silicon carbide is highly conductive. It's that is thermally conductive. It can hold off voltages at much thinner layers, and it is when it is doped, it is more effective as an electric conductor, so it generates less heat. It switches that power at much higher frequency, which is advantageous when you're doing the power processing, because a lot of the other components are very sensitive to the switching speed, and usually higher speed means smaller. So you get advantages with silicon carbide that everything gets smaller because it's generating less heat, so you don't need as much thermal sink area. All of the secondary components are much smaller. So even though silicon carbide is still more expensive than silicon, the rest of the package can be much less expensive. So, advantage silicon carbide quite strongly. This was recognized back in the 80s, but the technology was so difficult and there was really no intrinsic drive to develop the technology that it just wasn't evolving very quickly. The government put money into it. DARPA put money in because of the advantages that they saw for the military. So DARPA helped start a company called CREE. So CREE, you may recognize as the company that was very big in lighting, still is big in lighting. So there are light emitting diodes. That's what the core of that technology is, right? Those diodes are based on silicon carbide in the main, particularly if they're CREE devices. They're almost going to be silicon carbide. So what was found is the silicon carbide back in the 80s and 90s, they couldn't make great material. They couldn't make it in big chunks. But they got to the point where they can make it good enough and big enough, and an LED is a tiny device, right? It's only a fraction of a millimeter or a millimeter on a size, puts out brilliant light at very high efficiency. So lighting became a real thing, and that's where the LED revolution for all lighting in houses, on cars, everywhere, that's where that technology came from. And a key part of that was CREE, an American company out of North Carolina, sponsored by DARPA back in the 80s, right? So, but essentially, this was all great because CREE was developing new materials. They were developing new processes. They could get bigger and bigger devices. And the work that they were doing on power out the side of the LED meant they built bigger and bigger devices, which moved from a couple of amps at, 50, 60 volts to 100 amps and maybe more at 500, 700, 900, 1200, 1700 volts, right? Real power, enough to drive a car or a big truck or anything, right? This technology came on. So by the teens of that 2000, that technology was really taking off, and that was again a big piece of why EVs suddenly became a big thing. The power electronics to do the motor drives and the battery charger circuits and the offboard power. I mean, those big systems you see for charging vehicles, they will have silicon carbide because there's a big piece of that where it converts your power to the form that you need to charge your car. That's all keyed off of silicon carbide. So there's a big need for the technology, and it was a big draw. And CREE was doing a lot of work in that area, but they weren't selling to the automotive company. As a company, CREE had decided that they weren't going to sell to the automotive industry because automotive is a very tough market. You have to deliver on time. If you don't and shut their line down, they'll penalize you like crazy. If you have failures in the field, again, warranty cost is a huge killer, and they will penalize you like crazy. Of course, the other bit side of that is because they're buying so much material from you, they'll say, oh, great, yeah, I know you spent, $500 million developing this technology, but yeah, okay, we'll buy the first 10,000 units. We'll buy those at $20 or 25 or $50 a piece. But, the first production year, when we buy 1 million of them, you're going to sell them at $15. And then the second year, you're going to sell them at 14. And then the third year, 30. I mean, they're going to take your efficiencies from learning and bulk production. They're going to take those efficiencies and they'll let you keep some of that profit, but not all of it. And so they're a tough market. And CREE stayed out of that market, but the board said, if you want to be in silicon carbide and remain a player, you have to go after that market. And oh, by the way, it'll really be good in the long run. So they actually split the company. CREE became focused on LEDs, lighting. And then they split off a company called Wolfspeed, and they brought in all new management who in a new set of management for Wolfspeed, management who had experience with the automotive market and automotive electronics, though that was all silicon based and mostly digital and analog, not power, which had its problems later on. But they did do big things and really move quickly into the market. And Wolfspeed was selling to everybody. And if they weren't selling modules, they were selling devices. If not devices, they were selling material, and they were selling to everybody. And they were making big inroads. Every quarter there would be another $1 billion worth of new market, new customer, VW, Jaguar, etc. Right. So anyways, there's big things moving forward, and the company basically said, we have to expand, which had been what the board had said, you have to invest. And the company, so Wolfspeed went from a couple of thousand people to 7,000 people. And with a lot of those focused on one, growth of the materials side and the fab side, but also market side and back end side. That was back end is what I was doing, which was power modules and meeting the needs of various customers, some automotive, a lot of other ones as well. But anyway, so big growth, big promise, quick moves into the market, all looking really great. And then you basically reach the point where there's a lot of recognition that there were problems, that inherently the big companies couldn't flip over to building low-cost EVs. They could build the bit high-cost ones, but they couldn't build the low-cost ones. There wasn't a huge market for the low-cost ones, and there were a lot of infrastructure problems with the low-end ones. And then there was another inherent problem. Even if the government said, oh, everybody has to buy EVs now, you can't buy an internal combustion engine. Well, where does the power come from, right? With an internal combustion engine, that internal combustion is from prime energy, right? From diesel or gasoline. In an electric vehicle, a battery is not prime energy, right? It's storing energy. It was generated somewhere else. That energy could be from wind or from PV, but it's usually from coal or nuclear or natural gas or oil. So and we weren't building new plant. We were replacing plant with wind and PV and some battery storage, but we weren't building out new plant. And then, of course, the other one in the more recent days is like the AI is eating up all the excess power that can be generated. So, where is that power going to come from that you're going to have your whole economy based on transportation system, which is electric based? Just wasn't practical. So essentially, everybody started moving away. For a while, it looked like the Chinese might be good or the Europeans might be good, but the Europeans had the same problem, right? In reality, the reality is they didn't have the power infrastructure. They had other inherent problems. And then on the Chinese side, the problem was, yes, they'd been building, coal-fired power plants out the, and EVs like crazy, right? But the problem with China is they'd been copying Wolfspeed's technology. So they had finally reached a point where they were competitive with Wolfspeed on the base material and the devices and the packages and whatnot. And Wolfspeed no longer had a market, right? So it might be a small market, but it's certainly not a significant market. So market collapsed, the income collapsed. Company basically had gone into debt for billions of dollars to build up their plant and bring in new people, and they didn't have a market for it any longer. So, went through a huge series of cutbacks. Actually, got rid of the management that had been brought in not that many years before. Brought in a new set of management who had some more experience with power electronics and automotive, but they had to focus on basically standing the company back up, getting it back on its feet financially. And that meant they had to cut the staff by over 50%. And, I was one of those people because I was working on new product and new customers, and those just were no longer going to be focal areas for a few years. So, that's where I met the end, and EVs ate my job. Wasn't EV because EVs are bad in themselves, but, the mixture of all of the things that were going on in the environment, and then the fact that you're talking about new technologies and huge investments, it basically pushed the company into receivership. And I'm sure they'll recover. I'm sure they'll be a big player, but for now, that's the end of my career there. I mean, as you can see, I'm not a young chick anymore. I'm 68 years old, and I live where I live. I'm no longer willing to chase jobs to the coasts or to Detroit or to Dallas or whatever. Just not going to happen any longer. So I've been trying to find, something in my route. But again, I'm a fairly specialized set of expertise, and that's not in this area. So I'm looked at pivoting and decided I'm not going to pivot career, but I am going to pivot my life, and I am going to go do a lot of other things. I'm going to do a lot focus on making and creating, kind of do other things than try and get a job. See if I can get a life outside of work. So my wife will tell you that I've been a bit of a workaholic for most of my career, and that's not always been great. So one of the things I am going to be doing is working on science fiction. I have written science fiction for about 30 years. I have 5 books out, e-published, but I have 4 others and more that I am working on, and I plan on working on those and getting them out there and maybe doing some updates and learning how to use all the modern tools. Have fun that way. So, a whole bunch of different things. So that's what the Unretired Engineer is going to be doing. So please, if you've liked this content at all, hit the like button and hit subscribe. I plan on being back about once a week, maybe a bit more frequently, and talking about all sorts of different things. If you have any comments or questions, put them in the comments and questions area, and I'll take a look and see what I can do to answer the questions. So have a great rest of your day. Thank you very much. Signing off.